Hey there, Math 2403. Welcome back. Here we are, Unit 6, video number 1. We're moving into inferential statistics, where we will basically be combining probability and descriptive statistics in order to make predictions. We'll start out with confidence intervals for the population mean. We'll do the case where we know the population standard deviation, or the case where sigma is known, and then we'll move on to the more practical case where we don't know the population's standard deviation, or when sigma is unknown. We'll come up with intervals for mu based off of sample data. And we'll be able to come up with ways to make decisions using these intervals. So let's get right to it. Here we are in our unit on single parameter inference. We've been estimating population values basically since day one of the course. Day one of the course, we talked about how X bar was our, typical estimate for the population parameter mu. And we also estimated sigma using S, or sigma squared using S squared. Sometimes we estimated the average with the median because we felt that that was a better representation. But typically we do use the mean. Some other estimates that we could do might be proportions. We could estimate the proportion of people that are going to vote in the next election by taking a sample and hope that that sample proportion represents the population proportion. And I'm trying to stick with the notation here. So the Greek letter that goes with P is pi. So it'll take some getting used to pi being a variable and not an irrational number. We can also compare multiple means. We want to compare the difference between the mean of the men in our class versus the mean of the women in our class based on some attribute, say midterm exam score. Or we could compare proportions, the proportion of women that passed our midterm versus the proportion of men that passed our midterm. Again, we'll use sample differences. We'll use lowercase p for proportions. We can also do the difference of X bars. Whenever we make an estimate, though, we'll never, or almost never, have our estimate match what the value is for the whole population. And typically we won't know what our error is because we won't know the entire population. So I just wrote sort of a general form here. The population value, I just made a generic symbol, theta. So I have some population parameter theta, and I'm going to estimate it with theta hat. And my theta hat will, most obviously have error. And our goal is obviously to minimize the error. So we want to use an estimate that, we want to come up with the best estimate. So for us, in the first section here, we'll be estimating the population mean mu with X bar. It turns out that it is the best point estimate for mu. It's kind of hard to evaluate what best means. It has to be typically unbiased and have properties like as you increase the sample size, you tend to approximate the value of the population, more and more accurately. So here are some attributes of an estimator. The expected value of our estimate should equal the value of the population. So this is like our mean of the means equals the mean of the population, as we were discussing back in the central limit theorem. So X bar is an unbiased estimate of mu in that case. It turns out that S is not an unbiased estimator of sigma because we had to make a sacrifice. S squared is an unbiased estimate of sigma squared, but S is not an unbiased estimate of sigma. So remember that whole n minus 1 in S in the denominator. That came about to force S squared to be unbiased with regard to sigma squared, but a consequence of that is then S is biased relative to sigma, but it's biased in a good way. It errs on the high side. So we at least understand what its bias is. It errs high. We can also talk about, say, the efficiency of an estimate, meaning that you can't come up with an estimate that is has more or less variability than the one that you have. And then we have consistent, and that's the one about increasing sample size gets you a better and better estimate. I just sketched out the proof for the expected value of X bar equaling mu, proving that X bar is an unbiased estimate of mu. I basically just ground through the algebra a little bit. The expected value of X bar is the expected value, and I just replaced the formula for X bar with sum of the x's over n. When you have a constant in your expected value, it can just factor out. So we want the expected, then sum of all the x's. We can take out the 1 over n. And then it turns out that the expected value of a sum is equal to the sum of the expected values. So this is just some algebra for us. Maybe you haven't seen this sort of thing before. Now we know the expected value of x. That has to be the mean, right? If I have a bunch of individual scores, on average, what do I expect to happen? Well, I get mu. And now, if I'm summing up a bunch of mu's, say n mu's, I can just write it as n times mu, and we end up proving that the expected value of the sample mean equals the population mean, which means it's unbiased. You can do a similar thing with you can do the expected value, my pen here, you can also show the expected value of S squared equals sigma squared using similar algebra. It's a bit more involved actually. I'm not going to do it here. Our goal here is to, when we estimate, we want to somehow come up with that error. But the only way to know what the error is would be to know the actual population value, which we almost never do. So we're in the situation of having to estimate the error. So we'll maybe put a bound on it. So we'll define something called a confidence interval, which is just a range of values that we think contains the population parameter that we're interested in. So in our case, we're currently talking about the mean. We'll calculate an X bar, and then we'll put a plus or minus on the X bar. X bar plus or minus some error, and that will be our interval. Our degree of confidence is defined as typically something like 90%, 95%, maybe 99%. We often use this 1 minus alpha to denote confidence. And then we have the opposite, or what alpha is, that's called the significance. But in confidence intervals, we think more positively. We're 99% confident that our interval contains the population parameter. So say I'm 95% sure that the mean of the whole population is within some range, and that range will be based on the mean of some sample data that I collected. In order to come up with this error term, we're going to have to do something with probability, I guess. We can use the normal distribution here. We've been using the normal distribution forever. This is just your typical, Z table here. There's Z curve with 0 in the middle. And we have been using cutoffs to determine the difference between typical and not so typical values for a long time. When we learned the empirical rule, we learned that 95% of our values are in the middle, and they range between +2 and -2. That was just the old empirical rule. Now we're going to define these z-scores as critical values. So the +2 and -2 are now critical values for confidence intervals. And the notation is z with a subscript alpha over 2, where alpha is defined above as the significance, which came from the confidence. So you have your confidence in the middle, and then you have your significance in the tails. And we split it in half because the thing is symmetric, and we'll have just as much error up in the upper tail as the lower tail. So basically think of a critical value as a cutoff between expected things and not so expected things. And often we define that as 95% of our values are expected, and then there's the 5% that is not so expected. So these values would be like 0.025. We also learned since the empirical rule that these scores aren't exactly 2. If you read your Z table for these values, you actually get 1.96. And this one is no longer -2, it's -1.96. So these are the cutoff values that we would use if we're talking about a 95% confidence interval. We'll use different cutoff values with different levels of confidence. If we're 99% confident, these z-scores will move out a little bit, and the z-scores will be larger. If we go down to 90% confidence, these z-scores will move in. I won't ask you to, on a test, give me the definition of a critical value, but here it is, sort of basically what I just said. The number that separates sample statistics that are likely to occur from those that are unlikely to occur. Back when we were talking about z-scores for the mean, we had x bar minus mu sigma over root n. This thing kind of came from the central limit theorem. Now, if you look at this equation, the numerator of the thing is basically error. It's the difference between what we calculated and what the theoretical value is for the entire population. So the numerator of our good old z-score formula is just error. It's a way to define error. And then we can take this formula and rearrange it as a way to calculate error. Error is equal to some z-score times sigma over root n. Now, we have some control over the z-score that we pick. This will be our critical value. This is a z-score that separates what's likely to happen from things that are not so likely to happen. And now we can have a way to estimate error. We can write these confidence intervals then as, notation like this, where I take my mean, my calculated mean, minus some error, and my calculated mean plus some error, and then I'm hoping that the mean of the whole population is somewhere in that interval. And I'll have some degree of confidence. So sometimes I'm going to create an interval that is correct, and other times I'm going to calculate one that's incorrect. And that will be due to the fact that sometimes when I take a sample, I get an unusual value. I get one of those strange, 5% of the population that's unusual, just by, sort of dumb luck. You can write your intervals as in interval notation as we would in math, lower bound and upper bound. And typically I see them, I think the most common way I see them probably written is with plus or minus. When you watch the news on TV or a news clip on the internet, you'll see them say, well, in a recent poll, 78% of Vancouver residents approve of more bike lanes in the city. And then there's a plus or minus, say 3%. So 78% plus or minus 3% is a common way that they would write their confidence interval. Now, that is a confidence interval for a proportion where we're at first going to talk about confidence intervals for the mean. Here's a little example. I'm curing concrete. So I want to measure something about curing concrete. I want to measure the number of kilograms of cured concrete per kilogram of carbon consumed in the process. So I pour 33 slabs of concrete. And I examine them or measure them in some way so that I can come up with the average of 15.5 kilograms of concrete per kilogram of carbon. I would probably also have calculated the standard deviation. I would probably have gotten an S out of that, but the data here doesn't tell me what that was. Instead, there's a question here that says calculate, or that we know that the standard deviation of the population is 2.45. So they're saying use this data to construct a 95% confidence interval for mu when we know that sigma is 2.45 kilograms concrete per kilogram of carbon. So in this example, we have sigma is known. Remember when we were doing the central limit theorem, We said when sigma is known, we would tend to use the z distribution, and when sigma was unknown, we would have to modify things a little bit and use the t distribution. So that's coming, in the next example. But for now, let's imagine we have a situation where we do know sigma. My sample means are going to follow a normal distribution because my sample size is large. I don't even need to know that the population is normally distributed. And by large, I mean greater than 30. Greater than or equal to, I guess. So from there, we know that we can use the z distribution. Even without knowing what the population is, the central limit theorem tells me that my sample means will follow the z distribution. So now that we have established what distribution to use, we're going to try to calculate the error for our x bar. Ultimately our goal is to get x bar plus or minus some error. Well, error is defined from the previous page as a z-score times sigma over root n. Which z-score? Well, that depends on your confidence level. So we're creating a 95% confidence level or interval. So 95% confidence tells me that alpha is 0.05. That's the significance level. 5% of these scores are significantly weird. If we're to try to figure out what the z-score was, just draw the z distribution. It depends solely on, whatever alpha is. We know that the answer is around 2. In fact, it is 1.96. We can look this up, though, in our table. The upper tail has an area of 0.025, and the lower tail has an area of 0.025. That's alpha divided by 2. And now we need to figure out these spots on the z-axis. Now to find these things, remember the z table goes to the left, so I really have to look up 0.975, right? I have to add 95. The 95 is just in the middle, so I have to add the 0.025 in the lower tail in order to get to, this spot here. If I had my z table that was negative, then I'd have a fighting chance. I could just look up 0.025 in my negative z table, and I'll get negative 1.96. But let's look this up. I do have a negative z table. Oh, sweet. So I can look up in my table. It was already highlighted, I think. I'm looking in the table for an area of 0.025, and it's right here, which corresponds with a z-score of negative 1.9 and 6. So we can go back to our table here. This spot is negative 1.96, and so is the other one is positive 1.96 due to symmetry. And now we can just calculate our error. Our error formula is that z-score, 1.96. You could use plus or minus, because when you're calculating error, you end up, it's plus or minus anyway. Standard deviation was given to us of 2.45, and our n was 33. We calculate this out, and I get 0.8359. And the units are just the units of the data, which were kind of ugly in this dumb example. This is, our error is 0.8359 kilograms of concrete per kilogram of carbon consumed in the curing process. So now we have our confidence interval. We had a mean of 15.5. Imagine we had 33 values. I just didn't list them all. And then I calculated the mean from those 33. Then we calculate the error in our estimate of, say, 0.84. And again, the units are the same. Kilograms of concrete. Maybe I should write it just to get in the habit of always putting units with a confidence interval. And I also like to add the degree of confidence. If this is my final answer, it's nice to remind me, which confidence interval is this. We could rewrite this, take your 15.5 and subtract the 0.84. You get 14.66. And then add the 0.84, you get 16.34 kilograms of concrete per kilogram of carbon consumed in the process at 95%. So this is another, perfectly acceptable way to write this. And alternatively, I guess you could just write 14 point, I guess it's like, maybe I should be doing some sig figs here. Maybe I should only be going to one decimal place. 14.7 up to 16.3. Again, kilograms of concrete per kilogram at 95%. I think the most common way to write these is here. I think personally, I like the second version the best. The third version requires some mathematical, background. The average person reading a newspaper might not understand this notation as an interval, but I think they would understand the first two. They definitely would understand the first one because it doesn't have any math symbols in it except for plus or minus. So I think that's why it's preferred over maybe the other two. Personally, I like the second version because it shows me that you know what you just estimated. We didn't know what mu was. We figured out what x bar was, and now we think that mu is somewhere in this interval. We're 95% confident in this. We might be wrong. When I studied my 33 slabs, maybe I happened to get 33 unusual ones that were unusually high or unusually low. And then when I put my plus or minus on my unusual value, I might miss the actual value for the whole population. There's a reason I don't call this a 95% probability interval, and I call it a confidence interval. That's partly to remind myself that this thing, isn't foolproof. And I'm really not judging this individual one. I'm judging sort of the overall process. This 95% is referring to me making confidence intervals over and over again. Like I had 33 slabs, I tested them, I had a mean of 15.5. If I did another group of 33, I'd get a different mean, and I'd have a different confidence interval. And another group of 33, I'd get a different mean and a different confidence interval. Well, some of these confidence intervals will be good, and some of them will not be good, based on those 33 values that I get by chance. I don't say there's a 95% chance that mu is in this interval. I say I'm 95% confident in my method generating an interval that does capture the population parameter. It's a subtle difference, but I want you to avoid saying there's a 95% chance that mu is in that range. Because if I got 33 other values, I'd get a different range, and I couldn't say there's a 95% chance it's in this range and a 95% chance that it's in some other range. That just wouldn't make sense. So that's a subtle little difference between, why we might say it's confidence rather than just saying the word probability. If I increase my confidence, what has to happen to this stuff? Like, let's repeat this question and be more confident. If we do that, the only thing that's going to change will be the z-score. Sigma is still the same, n is still 33. Our cutoff values will be different. So these z alpha over 2s will be different scores. And I wrote 95 here. This should be 99. So in my tails, there's 1% in the tails. So alpha over 2 is half of 1%, so 0.005. Where alpha over 2 is the actual area. We just need to figure out where these values are. If we have our negative z table, certainly we can go and look that up. We're looking up 0.005. I guess it'll be further down in the table here. Maybe we can find it. 0.005 is somewhere around here. Negative 2.5, 0, 1, 2, 3, 4, 5, 6, 7, or 8. In fact, that one happens pretty frequently. If we look at our positive version of this table, it was exactly halfway in between. So our z-score is 2.575. We can actually add 1 decimal place of precision. If we went back to the negative version, you could see it's between these two, but it's exactly halfway between those two, which means we're between these two. So negative 2.575. I lost a page here. So it's positive 2.575 and negative 2.575. And then we can just recalculate the error with 2.575. And our sigma was 2.45. And our n didn't change. We're just constructing a 99% confidence interval for the exact same data. We get 1.098 kilograms of concrete per kilogram of carbon consumed in the process. So that's our error. It's 15.5 plus or minus 1.1. And we're doing this at 99% now. The actual mean is somewhere in this interval. We hope. We're 99% sure. You notice what happens, the difference between the 99% and the 95, it got wider. So in order to get more confident in my answer, I needed a wider range of values. So being more confident ends up having a wider range, which might not be as helpful. Sometimes this error ends up being so wide that it becomes, useless. If I want to make a 99.9% confidence interval for the results, for the mean results of your midterm, I could say, oh, I'm 99.99% confident that the mean on your midterm is somewhere between 10% and 100%. Now, as I could be 99.99999% confident that it's somewhere between 0% and 100%, but then it becomes completely, useless to me. So I will then sacrifice some confidence in order to get an interval that's narrow enough to be useful. I'd rather be 95% sure that the mean of your midterm was somewhere between 75 and 80 than be 99.999% sure that your midterm average was somewhere between 0 and 100. So we can kind of set our confidence based on how wide those intervals will ultimately be. Like if we try 99% and it's too wide, cut it down to 95 or 90. Those tend to be the typical choices, though. It's rare to see anyone publish some data where they have a 87% confidence interval or a 92% confidence interval. I know textbooks will ask for such things, but in reality, no one ever uses those. And I'd be suspicious if they did, because I'd wonder, why did they choose such a unusual choice when 99 and 95 and sometimes 90 are the standard. You might go a little lower than 90%, say in a social science, where you have so many variables and it's really hard to come to conclusions on things. You might be willing to accept 80% confidence intervals, for example. But in most, very well-controlled scientific experiments, we would use 95 or 99. We can do this stuff in Excel. You'll find that Excel has a nice function for doing these confidence intervals. I'll just put it here in the notes for you. You can just calculate the error. And in Excel, the function is called confidence. And if you're doing this Z version, it's confidence.norm. And its parameters are just whatever alpha is, whatever sigma is, and whatever n is. And it will just spit out this 1.098. You don't have to go through the trouble of calculating critical values. You just tell it alpha, sigma, and n. I have a worksheet already open here, I believe. It's our same example. So I basically did the example that we just did using Excel, and I'll post this for you guys in case you ever want to solve your questions using Excel instead. First, I did the question sort of the way we solved it, where I wrote down what is our confidence, what was alpha over 2, and then I calculated the Z-score. And then I manually calculated the error with my own function. So we used this Z-score formula before. It's norm.s dot inv, because I'm going backwards. I'm giving it a probability, and it's giving me the z-score back. I put absolute value on it just so that I get the positive version. Just like we saw when we looked up 0.025 in our z table, we had negative 1.96. So that's sort of the old school. This is the way we solved it, by hand, essentially. But instead of looking the value up in the table, I used a function. But we don't need to do all that work. Basically, you just need to know this one line. I put it in bold here. Confidence norm, put your alpha in. 95% confidence means that the significance is 5%. Input your sigma, input your n, and there it is, the error. Then I just added and subtracted it from the mean. The mean of the problem was 15.5, and we came up with our interval. It was easy to then repeat it for 99%. You'll see that the numbers are matching what we had done in our by hand calculations. And I even put a note that you end up with wider intervals with increasing confidence. This problem that we just did, though, as much as it seems somewhat realistic, isn't very realistic. I mean, what are the chances that we would know sigma? Like, that is really fishy. Like, think about what we just did. We are estimating the mean of the population. So we didn't know what mu was. How the heck would we know what sigma is if we don't know what mu is? Remember that sigma is the average distance away from mu. So how would you ever get that without knowing the mean of the population? So this is a very theoretical example. Like it works, it fits the central limit theorem, but in practice, we don't know sigma. So then we have to calculate an estimate for sigma. We would calculate S from this data set. And then to fix things with the central limit theorem, we would use the t distribution instead of the z. So that's where we're sort of headed. We won't use this confidence norm very often. We'll use another function called confidence t, because that's the more realistic situation. Heading back over to our notes. In every question we've done since the beginning of the course, I always told you what the sample size was. But what if you haven't collected any data yet? What sample size should you collect in order to gain or to achieve some level of error? Like, I want to make sure that my error is no bigger than some amount. Well, in that case, you can basically take that old Z formula or take your error formula, either way. We're now used to seeing this formula. The error is Z alpha over 2. Sigma over root n, and then we can just rearrange the formula for n, solve it for n. So maybe multiply both sides by root n. And then divide both sides by e. And then square both sides. And you get this. Now we have a formula that will generate the sample size that we need to achieve an interval or an estimate that's within some amount of error that we can preset. And we can also preset how confident we want to be. When we do these calculations, we want to always round them up to be conservative, err on the high side. The only real problem with this formula, if you look at the thing, is that it also has that issue of sigma is in the formula. This is the sample size that you need to collect in order to estimate mu with some degree of error and some degree of confidence. But in order to do that, you have to know what sigma is. So we're going to estimate sigma in most cases. And we'll estimate in such a way that we just err on the high side. And if we err on the high side for this sigma estimate, well, then we'll make sure that we're sampling enough to achieve the level of error that we desire. The example that we were doing, we did a 95% confidence interval for the mean. And this was our answer. It was 15.5 plus or minus 0.84. And that was at 95%. So I'm just reminding us that value. But what if 0.84 was too big? We couldn't live with that. What sample size should we have collected in order to get that error down? Like, obviously, it'll have to be bigger than 33. If we take a sample that's bigger than 33, we'll ultimately get a smaller error. So what sample should that have been? Well, we had just derived the formula. N is some z-score times sigma over the error squared. And I said, let's make sure that our error is at most 0.5. Like, we had an error of 0.84. We can't live with that. It's too high. Well, to calculate this, I want to maintain my 95% confidence. So I still want to continue to be 95% confident, but I want to make sure my error is down to 0.5. So my z-score isn't going to change. The z-score that goes with 95% is 1.96. My sigma hasn't changed, 2.45. My error now needs to be 0.5. And we calculate that. I get 92.23. So make your sample size 93. Round it up. In order to get the error down from 80.84 down to 0.5, I should have poured 93 slabs of concrete and tested them instead of doing 33. So here's a case where money starts to be the real factor. Money and time. Do you have enough time and money to sample 33 of anything? Or could you live with now an error of 84, knowing that you could only afford to do a sample of 33? So oftentimes you'll calculate the sample size that is desired. This is your starting point, and then you go, can I afford this? And if I can't, well, then maybe you'll go, well, maybe I can live with an error of 0.6, and then you'll calculate this, and then 0.7, and you'll calculate this, and you keep messing around with your error until you find, what you can afford. You could mess around with your confidence, but it doesn't change the amount that much. This value, it's 1.96 for 95%. It's 2.454, or sorry, 2.745. Was it? I forgot. For 99%, 2.575. There isn't a huge difference between 1.96 and 2.575. And even if I go down to 90%, it will make this number a little bit smaller, but it doesn't have a huge impact on it compared to the denominator. So usually that's what you have to mess around with, is you have to sacrifice error in order to get a sample size that you can live with and afford. I mentioned this earlier about the meaning of confidence intervals. I lost my spreadsheet for this, but I created a spreadsheet where I would generate 100 random values, and it came from a normal distribution that I knew the mean of and I knew the standard deviation of. So I knew mu, I knew sigma. I generate 100 random numbers from there. Then I calculated X bar. So my first experiment, I got a mean, say here, and then I put the plus or minus on it. And then I did the experiment again. I generated 100 random numbers. I got a mean here, and then I put the plus or minus on it. And I just plotted it so you could kind of visualize what this is all about. And then I did 100 random values, and I got another mean, say here, and then I put the plus or minus on it. And then I did another 100 random numbers, and I got a mean right here, and I put the plus or minus on it. And in all the cases, I was doing 95% confidence. You'll see that there's quite a bit of variation in those things. And in one case, I blew it. Here's a data set. I collected 100 random values. I got an X bar here, and then I put the plus or minus on it. And you'll see that it misses the mean of the whole population that the values came from. When I generated my 100 random values, they just happened to be high. Like I got 100 that were higher than usual. And that messed up my mean, and I missed. I came up with a confidence interval that did not contain the population value. But I was pretty good all the way along here. Like, I only failed in one case, and I did it 20 times. So 1 out of the 20 times I failed, 5%. It worked out perfectly. I wish I still had the spreadsheet, because you probably don't believe me. You probably think I just rigged this, because it wouldn't have to be that way. I could have generated 100 of these things, or 20 of these things, and they all might have worked. Like, it might not have failed until the 23rd one. So I got lucky that I had one fail in the first 20, and I didn't have two fail, which could happen, but just not very often. But this is supposed to illustrate the procedure. You collect some data, you construct a confidence interval, but in real life, you only do it once. You aren't repeating it over and over again. But if you could, your results would look something like this. And that confidence then is a confidence in the method rather than, I don't say there's a 95% chance that the mean is in this interval. I say that there's a 95% of all intervals have the potential to contain the population parameter. And we talked about this, increasing sample sizes reduces error. You can also increase confidence to reduce the error, but it doesn't have as much of an impact, especially because you don't have very many choices for what you pick for confidence level. Now let's do the ones that really matter. In real life, you don't know sigma. When you're trying to estimate mu, you don't know sigma. And when that's the case, we modify the central limit theorem and we use the t-distribution instead. And instead of having sigma in our formula, let's just estimate that with s. And S is a bit of an overestimate of sigma, like it is biased in that way. So if we're going to err one way or the other, we're going to think that there's more error than there actually is, rather than not as much as there actually is. So we have a new formula, but we can now just repeat all the stuff that we just did. We'll do an example where we calculate the error in the case where sigma is unknown. The only other little glitch we'll have is sometimes you can't use the t-distribution, and that occurs when the sample size is small and the population is unknown. But if your population is big, you're good to go. And if your population is small, but you know it's normally distributed, then you're good to go as well. That's what this is saying. Either the sample is from a normal population or we have a big sample size. If we meet those conditions, we're good to go with the t-distribution. And remember, when you're reading that t-table, it was degrees of freedom of n-1. So here's an example. We're liquefying coal, and we're keeping track of nice units again. The kilograms of distillate synthetic fuel produced per kilogram of hydrogen consumed in the process. So we're getting kilograms of fuel per kilogram of hydrogen. And we get to assume that this data is bell-shaped or normally distributed. So we do a test, and we take a few samples here, and we measure the kilograms of fuel produced per kilogram of hydrogen consumed in the process. And here's our data. It's a really small data set. 2, 4, 6, 8, 10, 12, 13 values. So our n is very small. First thing I do when I see a problem like this, and it tells me to find a confidence interval, I ask, do I know sigma? And in this case, sigma is not known. Then I look at the sample size. N is small, which could be trouble. But the population was given to us. The population was, they told us, was bell-shaped, so we'll say is normal. And then this tells us that we get to use the t-distribution. With n-1 degrees of freedom. This confidence interval using the t-distribution is pretty robust. Even if the population isn't normal, if it's just sort of kind of normal, it's been shown that this is a pretty reliable method for, determining error. So a lot of people fail to even think about any of this stuff, even though it's the most important thing we do. Anyone can calculate these confidence intervals. Were we allowed to use the model in the first place, which is the thing that is often overlooked. So sometimes stats are bad due to that, where people just, they know where the function is in Excel and they use it, where they don't stop to think about what they should have done and were they allowed to do it. These formulas are based on those, pretty theoretical central limit theorem formulas. So, but that often gets overlooked. Plug these 13 values into your calculator and calculate the mean. I ended up with 15.52 kilograms of fuel per kilogram of hydrogen. And I came up with a standard deviation. Remember, you use S here because this is a sample. We've only studied 13 things, of 2.43 kilograms of fuel per kilogram of hydrogen. And just so we don't forget here, N was 13. And that's why when I said it was small, it was under 30. To calculate the error, we said we're going to use the t-distribution. So our formula for error now is a t-score alpha over 2. And it gets multiplied by the standard error, which is S over the square root of N. So we just basically need to figure out what t is. So make a little sketch, find your critical values. It says 95% confident, so alpha is 0.05. So we have 95% in the middle, and then we have these tails that will have alpha over 2 or 0.025 for an area. And then you just need to figure out what score goes in these spots. It's symmetric. You might not remember that the t-distribution works to the right, so it's actually easier to find this positive value. I think that's why the table, in fact, is to the right, is so that you end up with positive values when you're doing these things. It's just easier for someone learning it. If I go to my t-table, get rid of all this junk, maybe. In our problem that we're doing right now, we have a degrees of freedom of n minus 1. So we had 13 minus 1. So we're going to be in row 12. And the area in the right tail, the T alpha over 2 on the right side, we're looking for an area of 0.025, which is this column of the table. And no surprise here, the number is pretty close to 2. You know how we've been sort of using, when we've been doing 95% from the empirical rule, we just called this 2. Well, the t-distribution lets us use slightly different values than that, depending on what the sample size is. You'll see that once you hit, into the 20s and 30s, it is pretty much 2. Once you get to a sample size of infinity, it matches what's in the Z table of 1.96. So the T table approaches the Z. Anyway, our critical value here is 2.179. And I lost my page. Don't worry, we can edit this out later. Won't, but we could. So we can write this on our axis here. It was 2.179 or negative 2.179. If you're an Excel person, you'd say t.dist. No, sorry, not dist. Dist is for probability. We knew the probability in this case, so I'd go t.inv. And we'd input, actually, I'll do it even easier. I know there's a function in Excel called t.inv. dot 2t. And 2t stands for two tails. So you have an upper tail and a lower tail. And in this case, then we don't have to even cut alpha in half. You can just put alpha in there. And then your degrees of freedom. So we'd put t dot inv dot 2t 0.05 and 12. And it should give us this 2.179. And then we can calculate our error. 2.179. S was 2.43. Put your calculator in stat mode to get that. And the formula still uses n, so use 13 here. Use 12 to find your t-score, but use 13 in your calculation here. I ended up with 1.47 kilograms of fuel per kilogram of hydrogen. So we take our mean of 15.52 plus or minus 1.47. And we're doing so at 95% confidence. Maybe you prefer to write it as an interval, 14.05 is less than mu is less than 16.99. This is rounded. I like this notation because it shows me that you know what parameter you just estimated. And then the units and label there. Excel has a function that does this error calculation for us, though. You don't even need to use this t stuff. You can just say the error equals confidence dot t, and you input alpha, s, and n. It knows to do. It will subtract 1 from n when it's doing its degrees of freedom calculation. So that's pretty handy. Especially if you already know S. So I can show you that. Example 2 in here. Again, I copied and pasted the other spreadsheet. So I started out with, yep, the confidence was 95, alpha was 0.05, alpha over 2 was 0.025. Oh, sorry, this is the sample size. Sorry, this is example 3. So we had our fuel values. I counted them. There were 13. I calculated the mean and standard deviation using Excel functions. Then I did my confidence was 95, alpha 0.05. And I did it the old school way, the way we just did it. Instead of looking up the critical value, I used the inverse function. And then I made the formula, custom to get the answer. But we didn't have to do all that. You can basically just use the bold here. The bold says plug in alpha, plug in the standard deviation, and plug in n. And it gives you the error. And then I just added and subtracted it from the mean up above. There's another feature of this where we didn't even have to do this. You already used the analysis tool pack back in like lab 1 or 2. And remember, you did some descriptive statistics and you got a chart that came out looking like this, where it gave you a bunch of statistics, some that we didn't even care about, kurtosis and skewness, but it had the main things in it. It had mean, median, mode, standard deviation, variance, max, min, sum, etc. But if you look at the bottom of that output, it also gives the confidence. The label isn't great. It says confidence level 95%. It's giving you the error. So this is basically all I had to do was input this data, and then Excel outputs this chart. I guess I could show you where that is. Remember, it's under data, and then there was data analysis. You had to you did do something to add it in. And then there are different choices under data analysis, and one of them is descriptive stats. And then the first box here, you input the values. So I went H1 to H14, and I highlighted the title. So I had to tell it that I did that, so it didn't think that that was one of the numbers. And then you have to remember to check a little box that says you want the statistics. I don't know why. And then the next box is, what confidence interval do you want? So if you wanted a 99% confidence interval, you just input 99 there. Or if you want 90%, input 90 there. And you click OK, and you get this as your output. So it's really nice. It's 15.5 plus or minus 1.46. 1.47, I guess. So pretty nice for doing those calculations in Excel. Highly recommend it. You really don't have to be that good at reading your T and Z table as long as you have, Excel available to you. I think that's a good place to stop this video. We'll continue on next time, and we'll make confidence intervals for proportions. And then we'll move into another topic where we're going to start hypothesis testing.